Hello there, this is an Algebra 1 video. It's Chapter 6, Section 2, and today we're talking about substitution. In our previous lesson, we were learning about how to solve a system of equations using the graphing method. I'm happy to report that in the next couple of sections, we'll be solving systems, but we'll be solving them by using algebraic methods. And those algebraic methods are going to be, the first of which is this one, substitution. So we're going to get started right away. And then hopefully it'll make all kinds of sense. So the key with substitution, if you recall the graphing lesson, is that in order for the point to be a solution, and the solution is always an ordered pair, the point where the two lines cross, the x-coordinate, the y-coordinate for both equations is the same. So based on that, we can use this idea of substitution, because substitution means that you can replace one of the letters with the equivalent expression into the other equation. That might sound really fancy, but let me just show you what I mean. It's not as hard as you think. One of the first things you have to do is that when you do this, one of the equations that you're given has to be solved for a variable. What I mean by that is that the variable has to be by itself. So in this case, the first equation has the y by itself, but in this case, the x and the y are on the same side. So this would represent a situation where the variable is not isolated, but the first equation is an example of it being isolated. So you can see in part A here, the do-it-yourself question, that the first equation is isolated, and in part B, the second equation is isolated. It doesn't matter which one is isolated, but you have to have at least one of the equations isolated. And it doesn't even matter which variable. In all of these cases, it happens to be the y, but it could very easily be the x as well. That's the first thing. And so what you want to do is you want to take the equation that's not isolated, and then you want to replace the variable, whichever variable is isolated in the other equation. So in this case, the isolated variable is y. So you want to replace the y variable in the second equation. So what I'm going to do is I'm going to say 3x plus y. Since the y variable in the second equation has to be the same as the y variable in the first equation, that's why we're substituting. So since this one is 2x plus 1, this is what it looks like before I actually substitute. This is the exact same thing as the second equation. It's 3x plus y equals -9. But now I'm going to replace the y from this equation with the y from the first equation. See, now my equation has all one variable in it, and now it's not hard to solve at all. So I get 3x plus 2x plus 1 equals -9. Subtract the 1 to the other side. 3x and 2x is 5x. And -9 minus 1 is -10. Divide by 5, and x equals -2. Once you find the x-coordinate, you can do the exact same thing and replace it again to find the y-coordinate. So the y-coordinate is equal to 2x plus 1. And since the x-coordinate we just found was -2, we put that in there. 2 times -2 is -4 plus 1, so y equals -3. The last thing is to write your answer as an ordered pair. X-coordinate goes first, y-coordinate goes second, and this is your solution. So it's that simple. So now I'd like you to try do-it-yourself number 1, and then we'll go on to another example. And in this case, this has gotten a little bit more complicated for us because now neither of the equations that we're given are isolated for a variable. They're both in standard form. So our job is to first and foremost take one of the equations and actually solve it for a variable. And I will tell you right now that the easiest way to do that is to pick, if possible, it isn't always possible, but it is in this case, to always choose the variable, because it doesn't matter if you choose x or y, but you always want to choose a variable that has a coefficient of 1. So this variable x has a coefficient of 1, coefficient of 2, coefficient of 3, coefficient of -4. So these 3 variables are probably not good ideas for me. So I'm going to choose the variable that has the coefficient of 1. So I'm going to take this equation and I'm going to solve it for x because that's the easiest thing to do. Subtract 2y. It's not the only thing you can do, but it is the easiest. So x equals 6 minus 2y. Now I have one of the equations isolated for a variable, and I can continue to do the problem just like I did in the previous example. So now, my second equation, because this is the same thing as that one, my second equation is 3x minus 4y equals 28. I then replace the x variable with the expression that x equals from the first equation, and then I solve for y. So 3 times 6 is 18. 3 times negative 2 is negative 6y. Minus 4y equals 28. Excuse me. Subtract 18 from both sides. Negative 6 minus 4 is negative 10y. 28 minus 18 is 10. When I divide by negative 10, y equals negative 1. Now that I know that y equals negative 1, I can go to my first equation, which is that x equals 6 minus 2y, and I can replace the y with the negative 1, and negative 2 times negative 1 is positive 2, so x equals 8. Write my solution as an ordered pair. X variable goes first, y variable goes second, and there you go. So that's how you solve when you have two equations where neither one of them is solved for a variable first. You have to solve for the variable and then continue. Alrighty? So now we're going to try this little guy. And what's going to happen here is that we're going to end up probably, we already saw before that we have a potential for different types of solutions. It can be the same line or it can be parallel lines. So we want to see how that works out. And that's going to basically happen if you end up with a true statement or a false statement. So, for example, this one's already solved for, so we're going to proceed like normal. So I'm going to take my negative 6x plus 3 times y equals negative 12. And then the y, I'm going to replace the y variable with 2x minus 4. And then I'm going to attempt to solve. So I get negative 6x. 3 times 2 is plus 6x. 3 times negative 4 is negative 12 equals negative 12. 6x minus 6x is 0. So I end up with negative 12 equals negative 12. Well, this statement is always true. So when a statement is always true like that, this is a case of infinitely many solutions. This is a case of consistent and dependent. This is a case where the two lines are actually the same line. So you have infinitely many solutions. And you can see that, like if you hadn't actually done it algebraically, you can see that if I put this in y equals mx plus b, I'm going to add the 6x to the other side. And then when I divide by 3, I'm going to get y equals 2x minus 4. So you can see they have the same slope, same y-intercept, so they're a consistent and dependent system with infinitely many solutions. But algebraically, you don't have to do all that, but algebraically, whenever you get a true statement like this, it's going to be always true, infinitely many solutions. If you get a statement that's always false, like 0 equals negative 12, then that would be a case of the parallel lines, and that would be an inconsistent system with no solution. So my guess is that for A and B, you're going to get one of each. So good luck with that example, and then we will go to our last example for this lesson. It's a very short lesson today. And it says, a store sold a total of 125 car stereo systems and speakers in 1 week. The stereo system sold for $104.95 and the speakers sold for $18.95. The sales from these two items totaled $6,926.75. How many of each item were sold? So we have to first and foremost create a system for ourselves. And so the easiest thing to do is to use x and y. So we have two types of things. the stereo systems, so we can call those X, and speakers, we'll call those Y. So what it says here that it stores a total of 125 car stereo systems and speakers. So the X plus Y is equal to 125. When you combine the two items, they sold 125. So that's the first equation. And then the second equation, which is the equation that deals with how much money they made, we know that the stereo systems, which is X, sold for 145. So basically 104.95 times X, so however many stereo systems they sold, times 145 is how much money they made off of that. And then they had 1895 times Y, because Y is the number of speakers, and every set of speakers was sold at 1895. So again, multiplication. And then combine those two profits, they made 6,92675. How many of each item were sold? Basically, what we have to do here is solve the system. So it's probably a no-brainer that we want to take the first equation and solve it for one of the variables. And in this case, since they both have a coefficient of 1, it doesn't matter which one you pick. So I'm just going to subtract X from both sides, and I'm going to get Y equals 125 minus X. Okay? Then I'm going to take my second equation, and I'm going to go 104.95X plus 18.95 times Y equals 6926.75. And since Y equals 125 minus X, I'm going to replace the Y in the second equation with 125 minus X. And then I'm going to solve. So we're going to get 1895 times 125. So this times that is going to be 2368.75 minus 1895x, because 1895 times negative x is negative 1895x, equals 692675. I subtract 2368.75, subtract 2368.75. So I have 104.95 from right here, and I subtract 18.95, and I get 86x. On the right, I get 6926.75 minus 2368.75, and get 4,558. Divide both sides by 86, and I get that X equals 53, which means I sold, or they sold, 53 car stereo systems. And then for Y, Y is 125 minus X, or 125 minus 53, which means that they sold 72 speaker sets. And then combine those, you get 125 total items sold. And that is how you solve that, guys. So I will let you do this last example, and once you have finished that example, you will have completed your notes for this lesson, and I will see you in class. And thank you for watching.